In this video, I'm going to prove this trig identity where n is a positive integer larger than or equal to 2. We have a product of sine of k pi over n equals n over 2 to the power of n minus 1. Before that, we're going to prove this lemma. So if you just treat it as a function, treat it as an equation, a polynomial equation, degree n, z as the unknown, w as the constant, move w to the left-hand side. Right-hand side becomes 0. Then we can just solve for z, right? Exactly n different solutions. So n different roots. So each root is represented in terms of capital R and phi, right? Where phi is the degree of w, right? W written in trigonometric form. And so first this lemma, right? So z to the power of n, right? Z written in this form. So z to the power of n equal r to the power of n times, according to De Morve's rule, right? Just multiply cosine n times theta, right? Plus I times sine n times theta, right? It says equal to w, right? W. But w is r times cosine phi plus I times sine phi, right? So accordingly, correspondingly, r to the power of n should equal to r, right? Both real numbers. So I can immediately solve for r, the nth root of big R, right? So n theta, also n theta, equal exactly to this angle, right? Of phi. Right, but not just phi, but phi plus 2k pi. Right, k is a positive, is any integer. Right, so that way, theta is over n phi plus 2k pi. Of course, k can only go from 0, 1, 2, all the way up to n minus 1, right? Because not n, right? If it's n, then we have what? 2n times pi divided by n, 2 pi. Right? It's the same effect as if k is equal to 0. Same effect. So we only go up to n minus 1. So in that case, I'm done. Right? I'm done solving for z, right? Treat z as an unknown, right? N different roots. So we're going to use this fact and construct, in order to prove this identity, I'm going to construct z to the power of n equals 1. Right, we're going to solve for z. But remember, 1 can be written in trigonometric form, right? It's treated a complex number, right? So its principal argument is just 0 degree, right? Length is 1. So 1 modulus is 1. Cosine 0 degree. Cosine 0 degree. Plus I sine 0 degree. So in that way, this is my capital R, this is my phi, right? So according to that result, can solve for z, right? Z is each root. Each root is equal to the nth root of capital R, that is 1, right? Times bracket cosine. It's an angle. This angle is n phi is 0 plus 2k pi. Right, that's the angle. Plus I times sine of and 0 plus 2k pi. So that is equal to 1 times cosine 2k pi over n plus I sine 2k pi over n. Right, that's my each root. K goes from 0, 1, 2 up to n minus 1. Perhaps I'll denote z as z sub k, right? Just to denote z naught is the first root, z1 the second root, so on and so forth. Right? So, in other words, if I can, so here's 2k pi. Right. So first I'm going to rewrite it into exponential form, right? E to the angle is 2k pi over n times I, right? So now I want to zk. First of all, rewrite this equation, z to the power of n minus 1 equals 0. And let's rewrite it into, factor it out. We have the formula, z minus 1 times z to the n minus 1 plus z to the n minus 2 plus all the way to z and plus 1. Right? This is factorization. And at the same time, since we have those many roots, right, meaning we can factor out into several factors, where each factor is z minus the first root, right? First root, z naught, z minus the second root, z1, all the way, z minus the last root, z sub n minus 1. And at the same time, I think I can rewrite, so remember each root is given by cs, so can be also written into z plus, what's z naught, is k equals 0, right? E to the 0, that's 1. Right, what z1 is e to the 2 pi over n I, right? And so on and so forth. The last root e to the over n 2 times n minus 1 times pi I. Right? So, like I said, the original equation, right, equivalent to this equation, right? But then I use factorization, right? Standard factorization, right? A to the n minus b to the n, right? 1 to the power of n, right? Standard factorization, and also at the same time using the roots factorization, right? These are the roots. Now, from this equation, right, can we just straight away say that since z minus 1, right, if we say z does not equal to 1, right, just get rid of z minus 1, z1, cancel them out, then we can say this part is equal to this part, right? But I want to make sure that they also equal to each other even when z is equal to 1. Can we straight away draw this conclusion? If we want to be more rigorous, maybe I can say this, right? Instead of straight away draw the conclusion, I rewrite z to the n minus 1 over z minus 1, where z does not equal to 1. Right? Just divide this over here. It equals this part. Right? Z n minus 1 plus z n minus 2 plus all the way z plus 1, right? At the same time, this also equal to, right? Divide this z minus 1 over here, equal to the remaining part, right? So equal to z minus e to the 2 pi I over n, all the way, z minus e to the 2 times n minus 1 pi I over n, right? When z is not equal to 1. But if we want to make sure that they also equal to each other even when z is equal to 1, right? How can we, perhaps we can say that because this function in terms of z, right? Is it continuous at 1, right? I believe so, because this function is just this function in terms of z, right? It's obviously continuous at 1, right? When z is approaching 1, right? Obviously continuous, right? So is this function in terms of z, right? So therefore we can say, as z approaches 1, right, their limit is equal to each other, which is equal to the functional value at 1, right? Maybe that's more rigorous, right? So then we can say that, okay, here's my conclusion. As z approach 1, right, their limit equal to each other, right? Each limit is the functional value at 1. So 1 plus 1. How many ones? N ones, right? equal to 1 minus e to the 2 pi I over n all the way. 1 minus e to the 2 times n minus 1 pi I over n. Now I'm going to rewrite it into a more neat format. And let's copy it down. So n equal, this time n equal the product where k goes from 1 up to n minus 1 of 1 minus e to the, I always have 2 in front of pi I. And so 2 times 1, 2 times 2, 2 times 3. So 2 times k is changing, right? K pi I over n, right? This is what I have. Right, k goes 1, 2, 3, 4 over. So this time I'm almost getting very close to this formula, right? I have n, right? The rest is find out 2 to the n minus 1. How can I? Perhaps now I can just, so let me just, n equal k 1 n minus 1. Let me just rewrite this part, factor out e to the, let me see, e to the k pi I over n, right? So I'm left with, so 1 now becomes e to the negative k pi I over 1 over n, right? So it's still the same thing, multiply together equals 1, exactly, right? Minus e to the, this time, k pi I over n, right? Still the same thing, right? Equal this thing. And so notice this is in fact can be written into, I think it's, so n equal k goes from 1 to n minus 1 e to the k pi I over n. Remember, this, when you write it as trigonometric form, right, we can happen to cancel out the cosine part, right? Cosine part will be gone, and we're left with the, I think it's the negative twice of I times sine part still remains, right? What's the angle? K pi over n. Right? This is easily verifiable. Just rewrite them into trigonometric form, right? So this time maybe I can, first of all, take out the 2, right? But 2, still there is a product, right? So meaning 2 times 2 times 2 to the power of n minus 1, right? So n equal 2 to the n minus 1 coming out. And product k goes from 1 to n minus 1. And I'm left with, first of all, negative I still remains, right? Negative I still remains. 'Sine k pi, 1 over n, 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 1 over n times e to the k pi I over n. Right. So now what do? Now I just, remember, I'm almost there. Right? We divide this over to there. N over 2 to the n minus 1. Right? But I'm not done. Still going to have to deal with negative I. Right? Because I don't want anything that's, right, I want everything is neat on the right-hand side. So the question is, how do we deal with negative I? Right? Equal. First of all, this product is easy to do, right? E to the k pi I over n. K is changing, right? So e to the pi I over n multiplied by e to the 2 pi I over n. So all we have to do is to sum up the powers, right? And the base is e. So this is easy to do. e to the right, k the 1 2 3, so sum them up. 1 2, sum them up all the way, n minus 1, right? So pi I stays, n is fixed, stays, right? This is what I have after product, right? I'm still left with the product. K goes from 1 to n minus 1 of negative I. Like I said, negative I can rewrite it into exponential form, right? The principal argument of negative I is a complex number, right? It's right down here, so it's negative half pi. That's the angle, right? So can be written into e to the negative half pi times I, right? That's its complex number, its exponential form, right? Then of course I still have sine k pi over n. So now let's just quickly work out this sum. This sum is easy. So n over 2 to the n minus 1 is equal to e to the so according to the formula we have half of n minus 1, this many terms, and first term plus last term, still have pi I over n, right, still have this, and multiply by e to the, so this product, product, right, has nothing to do with k, but still I'm going to have to multiply it n minus 1 many times, right? So that becomes just multiply to become e to the raised to power of n minus 1. That is negative half of n minus 1 times pi I. Right, that's the result of multiply this out. And so this product, let's copy that down. Product k goes from 1 to n minus 1. Sine k pi over n. Right? So now what I do? Now I just say this time n over 2 to the n minus 1 should equal to e to the, this becomes what? N. So this becomes n, right? N cancel out. And half e to the half of n minus 1 times pi I. Right? This no problem. Also multiply by, copy this down. Negative half of n minus 1 pi I, right? Multiply by product. K goes from 1 to n minus 1 sine k pi over n. All right, this time I should easily have this is exactly the opposite of that, negative. Now, the multiply becomes e to the 0, so becomes just 1. All right, 1 times. All right, so this product this time equal n over 2 to the. Right, so this is exactly this product, right? Pi over n, 2 pi over n sine. Exactly my desired goal.